This is the end of the year, so I wanted to cover a very exciting topic. It's robotics. AI and robotics. A lot of things is happening on the modeling side, also on the business and industry side. So I think it'd be a good idea to give you an overview and maybe hear from you if you are working in this in that area. I'll explain the title later on if you don't know what is a VLA. But by the end of the talk, I hope that you have a good overview of what's going on in robotics. So I'll cover a few topics, go over a brief history of robotics, what we call modern robotics, which is in fact the classic classic robotics, the data that we use, explain what are VLMs and VLAs, the learning methods, and discuss briefly what's going on in the industry on the business side and future directions of robotics. So you might have seen this, on the internet, around you. So these are like the humanoid robots. We don't see them I mean, they're not very common yet, right? At least we see them on the internet. You have the Tesla robots. So Elon Musk talks a lot about the Optimus robot, with the Boston Dynamics Electric Atlas robot. So they were quite famous in the past. They had this robot dog, and I think they are owned by Samsung now. Unitree G1 is a robot from China that here you can in fact buy online for the cheapest model. I think it is $21,000. You can order online, and maybe it'll be delivered in a month. Right? So you can have a robot like this at home. We have something called Agility Digit. I know a bit less about that. The Figure 03 is a startup also doing humanoid robots. But they're not all humanoid robots. So you have, we'll see like other kinds of robots later on. So a brief history of robotics. So robots have been around for a very long time. So if you go to Wikipedia or other sources, you see that, in at least 400 BC, you have a Greek mathematician, a philosopher called Archytas, who supposedly had built a mechanical pigeon made of wood and was able to fly. So I don't know if it is what it was written. The water clocks, Leonardo da Vinci built a mechanical knight. In the 18th century, you have the Turk that could play chess. And later on, it was revealed that it was not really a mechanical Turk. There was a person hidden in a box under the chessboard, and who was playing chess, in fact. The term robot was coined like a bit more than 1 century ago by a Czech playwright. In fact, it was his brother. So it was robota came from the Czech word. So it was used in the play. He was a playwright. Isaac Asimov, that you must know as an author of science fiction, but also a professor, designed the 3 laws of robotics, right? Like do not harm, and etc. 1948, at MIT, the field of cybernetics was created. The cybernetics is used to control robots. So all this theory about feedback, design, and so on. The first 1954, the first robot patent was filed for industrial robots, and then it was deployed at General Motors a few years after that. Or in between, of course, after World War II, you had the field of at the same times. You had the famous conference that created the field of AI at Dartmouth, the Dartmouth conference, so that created the field of AI. So robotics and AI evolved in parallel, even though they didn't they merged only like very, very recently. So Unimate was the first industrial robot. Well, the patent was in 1954. It was granted in 1961. It was deployed in the 1960s. Well, so I think first in General Motors. So then I'm going to skip now some of the like Shaked robots. You can see that on the internet. The first like robot arm, so it's just like a robotic arm that could like touch objects and carry objects. The robots, and so you have all kind of robots in Japan. So Japanese were very interested in robotics, and also in AI. So you have a Honda robots, the SMO robots. The Mars Pathfinder is a kind of robot, right? You have an autonomous vehicle on Mars. I'm not sure if it's like remote control or purely purely autonomous, but you have the Mars Pathfinder. At home, you might have a Roomba, right? A successor of the Roomba. So you can do simple things, but I mean, you can replace a vacuum cleaner. You have the DARPA challenge in 2004. So it's more for autonomous vehicle, it's from point A, from point A, from point B without the driver. The Watson, so Watson is not, it's more like AI related, but you could say it's kind of a robot chess, could do like a play chess too. You have Atlas, the first robots, and then I go quickly the Spot. So Spot, commercial Spot, maybe the robot. And RT1, RT2 will go over these two models. They come from Google and joint ventures with some universities. And then more recently, we have what they call, so more like this is more on the modeling side, what they call like diffusion policy. I mentioned that briefly. Open VLA and Pi0, these are also like, these are the first, these are like, first like VLA models. Groot and one from NVIDIA. This we're going to go cover this in this presentation. And the first like pilots in factories with modern robots, and most recently Gemini robotics, and many others. Because it's very rich history, so it's been going on for a very long time. And but why now? Right? So first, I'd like to start with what we call modern robotics. So modern robotics is not, in fact, is the classic robotics. So robotics that has been done maybe since the 60s, right? So I won't go over all the details, but you see you get the flavor of. So this is like a modern textbook on modern robotics. You can check it online. I think you can even like maybe it's even free. You can get the PDF, and you can if you read the chapters, it's more like math, physics, maybe like classical mechanics. So you have it's more like so it comes from the field of some of it comes from cybernetics. So you have very difficult feedback controllers. So you really want to model like everything, the points, the objects that you want to model to model the dynamics. So you have differential equations. You have the position, speed, accelerations, and so on. And you try to model this accurately, and you have controller, right? That you control and try to influence the trajectory, for instance, of it would be like a robotic arm, for instance, right? So and a lot of it is what they call a proportional integral, like feedback that they try to model, right? You have a controller and you control the arm. So you have to model torque and so on. So all these things are still, many of these things are still useful, right? So it doesn't mean that the new robotics is replacing everything. Some of it is still useful, but some of it is getting replaced. So how is it getting replaced? It's here. So this is a comparison. So classical robotics, or what we call modern robotics, and the deep learning robotics, so the new robotics. So different dimensions. I'll go over some of them. The programming approach first is rule-based with explicit instruction, so that follows these equations, right? And whether deep learning is learned from examples, from data, from experience. Right? Experience generate data, and it's how these models are calibrated and learned. So learn a control method, right, has hand-coded coded algorithms for each task. So usually you have to rebuild a new set of equations, parameters, and so on, because the robot is not learning. So you have to define these parameters for the robot, right? What's deep learning? It's learning with neural networks, right, today. So adaptability to the classical robotics is it needs to be reprogrammed for each task. New robot, each task, and so on need a new program. So you have to do it from scratch. Hopefully, the deep learning robots can be highly adaptable. You don't need to reprogram everything. Right? It can adapt itself to unseen situation, new objects, new environment, and so on. Development process. So after deriving the equations in classical robotics, you have the engineers have to write the code, right, to program the robots. Whereas for deep learning, we train these robots on large data sets on demonstrations, right? So we don't need to write the step-by-step logic. It's very similar to language, right? So before, you needed to be linguist, so you have to teach the model the grammar, vocabulary, etc. But now, these ChatGPT and so on, they use deep learning, and nobody's teaching these models grammars and so on. Right? Uncertainty. So modern robotics. So when something is a bit different, unexpected situation, these robots really they fail. So they struggle with unexpected situation. Why? Because everything is hand coded or hard coded, and so the new robots should be able to hopefully to handle uncertainty better. Computer vision. So now we made a lot of progress in deep learning in computer vision. Same thing for object recognition. Time to deploy. So for modern robotics, it's if the environment is the same, the task is the same, it's easy to deploy. But this is the new task, then it takes longer, right? So deep learning, it depends. So in fact, these robots are not deployed yet. I mean, they are still experimental, so it might take a while, in fact, to deploy these models. Computer requirements. So modern robotics just use CPUs, but it's not like data intensive. It's just like simple equations to solve, and so everything's hard coded, so just CPUs are sufficient. Whereas for deep learning, sometimes GPUs may be required. Training data, so only for deep learning. So we do like an example of pick and place, so like robot arm. So from one coordinate, move the gripper to another coordinate, and you have to tell the gripper where to go, right? The deep learning, it will find the target XYZ by itself, right? You'll give instruction, right? For instance, you can say, pick up that box and put it on the table, and you don't tell it XYZ, right? The precise coordinate, but the robot will understand where to put what the table is and where to put the box on the table. So the strength of the first approach is kind of predictable, it's interpretable, right? You can look at the code, exactly the equations. So it's really you really know what's going on. It works well in structured environment. It's in the factory, or the task is really well defined. Painting a door of a car, or assembling two industrial parts. And there's no training needed, no training on data needed, right? The strength of deep learning is that it can handle complex unstructured environments. It can adapt to variations, it can learn extremely complex behaviors, and hopefully can generalize across similar tasks. Okay. For weaknesses, So it's kind of the opposite of the strength. So this for modern robotics, a bit brittle. So if it's something is unexpected, for instance, the object is different, right? The object is bigger or smaller, different shape. He might not know what to do because it has to be reprogrammed. And hopefully, with deep learning, it can adapt, right? But the weakness is that it's a bit of a black box, a bit of like these deep learning models. Uh, it uh, it needs a lot of training data, right? It can be expensive for computation, right? It needs a lot of GPUs to train and so like the current large language model, right? And it could also probably hallucinate like the large language models, right? For sensing, so I think the both use sensors. I mean, better sensors is usually better. Probably the deep learning models maybe can use imperfect sensor, cameras, or like noisy sensors. For motion planning, they can most learn it, but as we said before, uh, modern robotics use like precise like geometric planning to do it, whereas the deep learning can learn it, right? Can learn the motion planning by itself. Training, so we saw that code versus data. Sim to real gap. Okay, sim to real. So some words that you is simulation to real life, right? Gap. Uh, so for modern robotics, it's not the case. I mean, it could be the case if you use a simulated simulation environment. I think it's still possible. But otherwise, if you really calibrated your model on real robots, there shouldn't be an issue. For deep learning, you will be an issue if your model has been trained in a simulator, right? So then you have to trust that your simulator is accurate and reflects reality. And we'll see later why we use a simulator is because we don't have enough data, right? So simulator can generate like an infinite amount of data. Error handling, so it has to be explicitly handled. And for deep learning, we hope that it can recover. The objects, so we have perception of objects, how it senses objects, how it sees objects. So it can learn by training in deep learning, but it has been pre-programmed in modern robotics. Understanding of physics, so one can be learned, one has to be explicit. Cost of mistakes, it could be low because there's no during development because no training involved, right? It can be high during training, right? Because you can make mistakes. Because yeah, some of the learning involves like making wrong moves, wrong actions. The robots can be damaged, but it can also maybe injure the people around, right? It can cause physical damage. Right? So the cost of training could be high with deep learning models. Scalability. So because each task needs to be programmed, so it might be difficult to scale this in robotics. So that's why we don't see the many robots around us, right, as of today. And hopefully in deep learning, the one we have like a good like humanoid robots, and we still do might start to see humanoid robots everywhere, right? Historical context. So the polar robotics has been going on since the 1960s, right? So it has been going on for more than 60 years now. And now deep learning has been really emerging in the past 5 years. So here, this is a typical like research robot that so this is like this gripping hand. So this Franka Robotics has been a leader in for robotic research to produce this kind of manipulation robots and grippers that people have used. The researchers have been using. So here you have two hands holding a red ball. Okay, and this is a kind of a workflow that you use. So typically, there's the people program a work like on a workstation. You have kind of software. ROS is the open source software to control this, and then you send instruction, to the gripper, and you have to define the position, the velocity, and so on. And you have a controller that control the arm robot. So a lot of research has been done on this kind of robot. And a lot of it is done what we call imitation learning. So imitation learning is you perform a task and you ask the robot to imitate, right? To follow the expert, right? So typically it could be for instance, it could be a human operator, right? You demonstrate a task, so you use a teleoperation interface, right? So you can like remote control like a gripper that you have seen before, and the gripper will replicate the movement uh, of the teleoperator, right? And then we collect all the data, right? So observations, the actions, and the outcome. Right? For instance, say the task is to pick up a red ball on the table. So the teleoperator will do it, right? So there'll be two set of tables, two set of red balls. Teleoperator will do it on his own table on red ball. The gripper will do it by mimicking the teleoperator, and the data will be recorded, right, on the gripper, and you see how it was done. So it be you follow the demonstration, and then say when we have that the sequence of observations, action, outcome, or the actions decided by the teleoperator. So you have a sequence so you have data, and then we try to replicate the outcome using supervised learning, right? So we know the action that the truth has been the action that the teleporter has done, and then we learn a policy. The policy means that from the observations, what is the action that we have to take, right, to get the design outcome. Okay, so this has most of the robots are trained this way, and when we are happy with the learned behavior, right, we try to test it with that human input. Okay. So here, like just how you to operate, you have a VR controller, you can use joysticks, motion capture, or those kind of things. On the executions that you just you follow the commands and what the sensors record the observations, right, to accumulate the data, right? And then we accumulate the demonstration data set. So a lot of data has been done, but this way was you do a lot of the data set have been accumulated. But in the past, each lab, which robotics lab, will have their own data set. They have different kind of robots, right? They don't have the same. So it's what they call embodiment. So the different forms of robots, and the task could be very very different. So what has been decided is that they try to collaborate. It's like, okay, let's put all the data together, put them in the one format, and see and then share the data among the researchers, so that we can maybe make more progress. So they were inspired by deep learning, right? By large language models, we use all the internet corpus, all the data on the internet. For ImageNet for vision, they collected millions of images on the internet to train these deep learning models. Right? Deep learning doesn't work if you don't have data. So if you want to apply deep learning to robots, they had to do the same. So accumulate a large robotic data on a large scale. So it was done with Google and on many major universities. So you see the kind of data they have accumulated. So they have merged 60 data sets. And so they have over 5,000 objects in the data sets. A lot of it is kind of is robot hands. You see that, for instance, the most common robot is the Franka robot that we have seen before. Then we have also robots, but you have also a remote control car and so on, kind of. But most of it is really manipulating objects. On the task that they try to replicate, to estimate, and picking, moving, pushing, placing objects, sliding objects, etc. And a bit of navigating and so on. Right? On the set objects, they have like so shapes, the object have different shapes. You have containers and furniture, like opening, closing drawers. So some of it is done with food, like so because you want to model like soft objects. Some of it of appliances, fridges, open the door of a fridge, restaurant size, picking up a spoon, using a knife, etc. Okay. So here I'll go over like one. So once they have these, when they have these models, they train two robotic models. So Google had like two models, RT1 and RT2, that you've seen in the historical timeline. So they're like a neural networks model, but trained on specific data set that they have assembled. And so for instance, RT1 was an open source model, 35 million parameters networks. So use a transformer architecture. So transformer is what you see in these large language models. So it was designed for robotic control. So we use visual input and instruction, right? And then produce some discrete action, right? So you can give instruction, and you look at images, capture on camera or images, and they perform a specific task. Okay, so RT2 is the more advanced model. So you use a VLM, and we'll go over the VLM a bit. I think in the next page or two. So it's more larger model, and RT2 is not an open source model. It's a Google model, also trained on so much more data than RT1. So they use RT1, but train them on this OpenX dataset, right? This large dataset, and see if the performance improves. So what is really like interesting is that because the large OpenX dataset is trained on different kind of robots, right? Whereas traditionally before we say, okay, we have one type of robots, we're trying to do a lot of experiments on the same type of robot, right? And then train it and learn the behavior, and see if it's going to be able to perform the task. So Google used to do that. They have using like many robots in parallel, but the same brand of robots, or the same type of robot, and see if you can learn the behavior. But here, because so it was really an open question to see, well, if we use data from different labs for different tasks for different type of robots, does it improve the behavior? And the answer is yes, right? So this is it was very exciting to know that you can these RT1X, RT2X had better performance than the original models trained on this large scale data set. Okay, so here I go over the VLM. Why is it useful for VLM? Because it's used for VLAs. So VLM is what they call like a multimodal large language models. In fact, you're probably already using large language models today, because if you use ChatGPT, Gemini, and so on, the latest versions, if you can use in your chat bot that you use, if you are allowed to upload an image, then it is already a vision language model, right? So for instance, ChatGPT, Gemini, or Claude, I think most of them, the recent models, you can upload a picture and say what is in that picture, or describe me what is in that picture, or you can ask things about that particular image, right? So this is already a vision. It's a vision language model, right? So you see it on the pipeline here, right? You have a text prompt. You enter the image, right? So the text prompt will be like the prompt ChatGPT. What is in the image? So what is done is that it goes through what they call encoders, so vision encoder and text, and here they call it a text, it could be a text encoder or text tokenizer. So they translate them into tokens, right? And then you merge them into like something that a large language models can understand, right? So you putting them into like what they call a unified embedding space. So simply like a kind of vector, multidimensional vector that merge the images and the text, right? And then it is fed into large language models, right? So models that doesn't understand images that directly. So these models have what they call cross-market attention. So it means that so they can understand the correlation between images and text, and this is learned from their data set. Right? They are trained on images with description, right, with captioning, and so on. So how they can understand relationship between text and images, right? So if your image has a dog, and you say, "What is in this image?" It will recognize that there's a dog in the image because in the training data set, you've seen pictures of dogs with the word dog associated to it. Okay. And the association is done by this cross attention. But we also do so a simple like large language model is doing cross attention between text. Once is a self text self attention, but now you can and then you have also self attention between images. Also, you can understand relationship between images. So, for instance, you have the most recent like models can merge images. Or you can say, I put one person, one person and one landscape, and you can say, put that person into that landscape, and he will do it and produce one image with both. Right. So this. So now it is how it is done. Right? So models like Nano Banana can do that. Right. And then it's producing this large language model will produce like a text, a number, or classification, and so on, right? So here, so this is like so first example of VLA vision language model, vision language action model, right? VLA. So this is a Groot and N1 from NVIDIA. So Groot, I suppose it comes from one of these Marvel movies. Right? I think there's a character called Groot, so it comes from that. So Groot N1. So it's a vision. So I think it's an open source model too. So what it does, so it's so from images and from instruction, right? So here you have a image. So this is the camera. So the robot has a camera. So it sees its own hands. And it has instruction. So the instruction you tell the robot, pick up the apple and place the apple into the bottom shelf, right? So then you want the robot to perform the task, right? So it goes through a vision encoder, it goes to a text tokenizer, right? Then it uses a VLM. It was like I don't know, it go to maybe it's open source, probably open source VLM models, right? That we've seen before. Then it will produce tokens. Okay, so it doesn't produce actions yet, right? Then in parallel, the robot has to know its state. So it has to know, for instance, the hands are on the table, or it has to know that the apple is in the right hand, right? Or maybe if the apple is not in the right hand, it has to know where's the apple, right? I might also want to know the history of past actions, right? What he has done in the past, right? So then it goes to some encoders. So it means that putting the form then into like especially like multi-vectors representation or tokens. Then everything gets into get it to mix into like a transfer model. DIT, I think, is like a diffusion model, transformers. And so you mix that, And then it goes into another new series of tokens. That it goes into an action decoder. So these things have to be decoded into different actions, right? So it could be a sequence of actions too, right? It could be one single action, but it could be a sequence of future actions. And then so the future actions could be moving from the apple. So it has to go from the from that point to the bottom shelf. So it'd be a sequence of action. This is not a second because the action could be every second, right? It could be each movement is an action. So you have a sequence of action. It's not only like move by one piece. Right? So ideally, you want to be able to move from the table to the bottom shelf and predict that. Okay, so this is a Groot. Uh, yeah, so this is what I've been described before. So here, so here it's really the same thing, right? So this is more like not specific to Groot, but the idea, So so camera, language, and the state, what we have seen, the different encoders. The state has a different encoders. Everything goes into a transformer VLM. That has an action head that you have seen, right? Then there are different types of models in the action head to go into actions. We go over this briefly later on. Diffusion model, flow matching model, and action chunking. So action chunking is really to produce a flow of actions, right? A sequence of actions, not a single action, and then it goes into you know then the robot is taking the action, right? Uh, so NVIDIA is very interested in robotics, right? Because especially in deep learning robotics, I think they were not that interested in modern robots because they don't have any anything related to their business. Because deep learning robotics needs a lot of compute, right? So not only to train the model, but even to simulate environments, right? So one of the issues that is in fact it's very expensive to gather to gather real data. Well, you need robots. It's very slow. It's so it's not that there's no on the internet. There's no standard robot data that you can download, right? So people have the idea of using simulation. So NVIDIA has invested a lot to do that. So we have ISAC. They had developed ISAC Lab. So ISAC Lab is really a lab to apply a model deep learning algorithm to train robots in the virtual world, right? In simulation, not. So you can do imitation learning, what we have seen before, reinforcement learning, etc. Whatever people come up with, it can be implemented in ISAC Lab. And it's built on what they call Omniverse. So it's a way to create typically it's like a 3D environment, environment, a bit like a 3D game, right? So and then you have a simulation layer. So how do you simulate objects? How do you simulate people? How do you simulate robots and so on, right? So then once you do that, then you can put as you saw the Unitree robot. Unitree robot can be put into the Omniverse environment and it can be a realistic Unitree robot. And then when it's there, then I can program my Unitree robot or then train my Unity robots to do specific tasks, right? And the idea is that you train in simulation and you deploy in real life, right? And because because it is in simulation, you can do you can train on a lot of infinite amount of data. Okay, so typically in the workflow we have different scenes, different kind of robots of what they call assets, configurations, right? It could be in a factory, it can be a hospital, and there's a different type of robots. It could be hospitality robots in a hotel and so on. So you set up all this into this virtual environment. You design the learning task. Let's say hospitality robots from a kitchen, for instance, like a customer is ordering food service. room service. Then you simulate a robot that will pick up the food from the kitchen and deliver it to the hotel room. So the robot will have to take the elevator and then by itself, knock at the door or ring at the door, and then deliver the food, go into the room and deliver the food. So all these things can be done in simulation, right? But the model has to be trained, right? So then NVIDIA has all the GPUs, and you can use that to train the robot, and you can train the model, right? You can train the model in simulation too, right? So this is what the sim to real is the simulation to realities that you could have a real robot, right? Then you have what you call state estimators. You have sensors, right? That you translate into observations that can go into virtual world, right? And tell it what to do, right? So inference is like giving the sequence of actions, then give some commands, right? An action controller, right? And then the robot will implement that. So in a perfect world, we should be able to do that. A real robot, right? So like in the example that I gave before, let's say a hospitality robot in a hotel. It will just like in real life, you have the real sensors and go into the virtual world where you have the hotel simulation. It has a digital twin, right? It have a twin of itself in the virtual hotel, and the program will tell him exactly what to do, right? Given the sensors, that's how it would work. Co-training. So co-training is something important is because we have there's a limited number of a single source of data. So we talk about human demonstration, right? But human demonstration is expensive, right? Because humans have to do it. It takes time. It can be expensive, and it might be very limited. So we want to train the robot. So co-training is you train from human data, but also we can train from robot data, from simulated data, what they say in the ASAC sim environment, but also use robot like self-play, doing explorations, and also people like have a lot of hope on internet videos on YouTube, for instance. YouTube, you have a lot of images of a lot of random things, right? So if a robot can just watch, you could watch the YouTube videos and infer and build like a training data. It could be a lot, right? Because you have a lot of like video data, right? So co-training means how do you mix all this data and how much weight you put on different data and build a joint policy training. So this is something that people use start to use. And but especially if you can use like internet video data and combine with virtual demonstration, it could be huge. A lot of in sci-fi movies, you see like let's say a robot watching TV and learning a lot of like random things, right? And from just watching TV, right? And so this is the idea of co-training. Reinforcement learning, in fact, is done mostly in virtual world. It's not done in real life. So reinforcement learning is simply that you try to teach an agent, a robot, by giving reward, right? Reward, so you do good actions, get the reward. The bad actions, there's no reward, right? And you train the policy using reinforcement learning. But because it's in real life, it's a real world, it is expensive. The robot could be damaged. For instance, it's making a mistake. It could cause injury and so on. So it is done in a simulation environment. So here it is an example done with ASAC. That's why people are very keen on doing it in simulation. It can be very slow too, because to train in reinforcement learning, you might need millions of experiments, right? Trial of errors, like millions of times. And sometimes it's not possible. right? It takes too much time to train. It could take years to train maybe a robot if you want to do millions of experiments. And this is for different tasks. So for each task, we need different kind of training, right? Hierarchical reinforcement learning. So this is also done. So this is the idea is that you have a higher level of policy, right? Let's say I want to travel from New York to London, and as the robot, know how to do it, right? Or or travel with me, or be my guide to go from New York to London. But then you want to divide it into sub goals, right? Now I had to go first to JFK. Right? I had to take an Uber to go to JFK. JFK, I have to check in with the airline. I have to go through immigration. Then I have to board the plane and so on. So different sub goals and each different skills, different sub goals needs different kind of skills, right? So from a high level policy, you have to go to mid level policy, right? Check-in at the counter is a different skill set than to call an Uber or once arrive in London to go through UK immigration and so on, right? You have mid-level policy, then you go down, you have low-level policy that really like at the control level, means that, if let's say the immigration agent in Heathrow Airport is asking for the passport, the robot has to be able to handle the passport, right? So it's really like at the microcontroller level. So hierarchical reinforcement learning is to have a task, try to divide it into subtasks, and be able to recall also which subtask or skills are required. And the idea is that you can reuse the task, right? Maybe going to immigration in the UK is the same as going to immigration in the US, right? So maybe the task that you learn can be reused. So here, before we mentioned diffusion policy, there's a little bit of math here, but here, so I tried to do there's a small video that tried to give you an idea, right? So it's really like how to generate action, or how do you learn action? So here it be for like a robot from going to one point to the other. So let me show the video. So a picture is worth like 1,000 words. So let's see if it works here. Okay, so you're going to from a starting position to target objects. So he start with a set of random actions, right? Then he's trying to learn by what they call like the diffusion policy, right? So it's a way to so it's a way to learn. So diffusion means that in diffusion you start from initial like a noise, right? And you can generate a target like destination or like the point where you want to reach, right? This has been used a lot in imaging, right? For images. So you might have heard of these diffusion models. So when you in generating generative AI, you say like generate a scene and so on. So a lot of these models use like diffusion models. So it starts from a point, it can generate from a specific step of instruction, you can generate a target image using this. So this is the same idea that instead of generating images, is generate actions. Okay. Okay. So flow matching also that we've seen before. So he say also like this is in the same spirit of a diffusion model, but it's really better. So let me show you a picture. Okay, you go from one point, you want to reach the target. You see all these arrows like in between, so it's different flows, and then you have different like trajectory, right? So different trajectory that it generates. Okay. So what is is doing? So is that this concept of flow? So what you see, we saw the arrows is like what they call vector fields, right? So it's also the same idea from like a noise go into like a target distribution, so target actions. Right? So the target, so all these things are calibrated using training data, right? Historical data, right? So you still need to train the model. But how you come from like a random models to like a specific models, you know, is done by flow matching, right? So flow matching, just like it it's able to calculate these arrows, right? To know where to go. So whatever you are in the field, so it's why it's called flow, right? It knows where to turn, right? To the direction of the target, right? Thanks to these fields. Okay. There's a paper you can learn about this for flow matching. It's something very used. The last thing that we've seen also in the description for creating actions. So it is ACT, action chunking the transformers. Okay, so it's a technique to produce a smooth action, right? Because you produce one action at a time. Also, it's very jittery. You'll see when so people if you don't try to predict a flow of a sequence of actions, the robot will be like. It looks the robot has a Parkinson, like it's moving like a very jittery movement. So what it's trying to do is try to predict like a sequence of action, k action at a time, right? This is what they call action chunking, right? So so here it's for one action at a time, right? It predicts, it takes a chunk of actions and predict of another chunk of actions, right? It's also is done with the transformer models, right? So there are a lot of so in other like AI models, there are but this is still like open. These are still open questions. So they use benchmarks, right? Like you have a lot of benchmarks in math, for AGI and so a lot of benchmarks. So they have also like a lot of benchmarks. So the benchmark tells you, what is the right answer to something, the right way to do it, right? And they try to have different tasks. To tackle a different kind of objects and so on, and to assess these models. Right? The problem is that we don't have that many benchmarks, right? And a lot of these benchmarks are very often about these manipulation robots, right? But there's no real benchmarks about, Optimus robots working in a factory, right? So this is not very common. Or like a humanoid robot working in a hotel, right? So these kind of benchmarks don't exist. So we have to find other ways to do it. So it could be even a simulation in the environment, etc. Okay, so I'm going RoboCasa is also so this is like a benchmarks done in simulation, right? To train a generalist robot, right? So they have here I think it belongs to Google. It's done by Google. So they have realistic scenes. Yeah, so these are scenes in the kitchen, living room or kitchen. They have different objects, right? Food, it could be knife, forks, and so on, and then different tasks, right? And then this is how you build a benchmark. But because it's done in the virtual environment, then you can generate a lot of data. Okay. Robot arena. So this is also this is also something very similar. But this one done. This is done also with more like grippers with manipulating robots, but different scene, right? Because the problem you don't want, like, for instance, the robot to learn, things that which are not relevant, right, to the task, right? It shouldn't be okay. The robot is going to use the left hand because the background is red, and use the right hand with the background is yellow, right? You don't want the robot to learn these kind of things, right? So and you want to make sure so the robot has not learned this kind of behavior. So these are like you can go on the website and see the performance of these different they're more like robots algorithms. Okay. Uh, So I'll go over like we're close to the end. So do you have in the industry, you have a lot of several startups that use, so they use the same ideas of VLA. So you have Pi 0 and Pi 0.5. This is a model from the company, a startup called Intelligence. I think a startup from Stanford. It can so a robotic system that can perform complex tasks in new. So really, what they want to do, performing complex tasks in entirely new environments, right? So that the model is adaptable. So as we've seen before, it combines various data sources, including direct experience, mobile manipulators, web data, verbal instructions from human supervisors. So use a VLA architecture that we've seen before to reason about long horizon multi-stage task, right? You can see long horizon, a long sequence of actions, and leverage different sources of knowledge for low-level action inference. Figure Helix is also another model. So you can see also it's also based on the VLA. It's a VLA model, but it has a VLM component that we have seen before. So it has so the idea unifies perception, language understanding, and learn control to overcome multiple long-standing challenges in robotics. So one single neural network. So you see that they do like similar things, right? So how the implementing practice might be a bit different, but you see that the idea. So it's really a system 2 and system 1 that you see in we have seen in psychology. Well, system 2 is the reasoning phase, right? In your brain, you think deeply about how to do your task. System 1 is something fast and reactive, but you take a decision instantaneously, right? Gemini robotics. So this is maybe the most recent. So they also use a VLM. So this from enable robots to perform complex tasks with advanced reasoning capabilities. So the models is like a reasoning model. So they call it ER for embedded reasoning. So it excels embedded reasoning. So it's reasoning, but also like is aware of its of objects and the physical has a good physical understanding, right? And then it goes into a VLA model, vision language action model that can translate the natural language instructions into robot actions, right? So the idea is that Gemini robotics can reason before taking actions, right? So it enables the robot to understand complex tasks. Right? So it's not simply put the wet ball into the lower bin. Right? We can give like a complex task, like cook me pasta, and it will know that it needs the stove, it needs the pasta, it needs the tomato sauce, etc. Right? So you can execute them into a structured manner. So really like really the idea is of a thinking robot. So it's really like the frontier of robotics today. Okay, so the last few slides I've talked about. So this is more like the research or like how it is done, the business side of robotics. So a lot of money has been raised. So across the world, like in the US, not in the US, but in China, in Europe, and worldwide, maybe like maybe 18 billion in 18 billion last year, and probably this year will be something similar. On the future projection, maybe the market could be estimated at maybe $500 million, like $50 billion, right? And could grow to 110, $150 billion by 2030, right? With a compound growth of 40%. So the projection, I know, are very uncertain, right? So here I just ask, this is from Gemini and this is from Claude, right? So you take an average of what they say, it gives you a rough picture of where we are going. So future directions. So here I'm going to conclude. So it's a very exciting area to be in. A lot of like interesting startups. Even Google is going to do that. I think Jeff Bezos. I think that is trying to do that too. Is going to he recently like. He did like he has a rocket company, so he has Amazon, but I think he's also it seems that he wants to do like robots. So probably, in my opinion, about winning things, and it seems that robots industry or in specific modern specific models domains. And I succeed first, manufacturing, industry, healthcare. You know that robots are used in surgery, right? They're not like smart robots, but they're used at least in remote control. It's a company called Da Vinci. So all surgeons now use, many, at least young surgeons know how to use robots now to do surgery. Agriculture, where you have issue of labor, right? Labor is difficult to find, so you can find. So I think it could be a priority to replace human labor. Hospitality, it's also that labor is difficult to find, and people might like to interact with robots, like in restaurants and so on. So there's an issue of where to find the data. So simulation is but is it going to work in real life? We don't know. A lot of startups, like people like Fei Li or Yan LeCun, they want to build world models. So really, simulated the world, right? So, but is it going to work? We don't know. Is the market too optimistic, right? Remember the self-driving cars have been around for a very long time, right? Since the DARPA challenge and so on. And now we start to see Waymo car, but it took a while. The Tesla is still not like self-driving, for instance. The Tesla has been around. So sometimes the roadmap can be a bit uncertain, right? So this is a quote from Jensen Huang, the CEO of NVIDIA. So what he says, friends of the chat, so because he said friends is come out, so he's talking to the audience. The ChatGPT moment for general robotics is just around the corner, right? And this is at the CES conference, and he was all these robots around him. Of course, NVIDIA is very interested, has a lot of stake in this game, right? Because they're selling these GPUs, all this compute and so on. The more compute we want, the happier they are, right? So maybe he's a bit biased here, but I think he's right that there's something very exciting going on. Okay. Okay, so here's just to advertise there's a coming book. One chapter will be on robotics. So the second volume on this on AI agents. So here before the first volume was more on the large language model agents. So here I focus more on AI agents going beyond like LLMs, so reasoning agents, robotics, and so on. So this is the focus on the volume 3 will be when we reach AGI, I write the volume 3, right? So I don't commit yet. Okay, so this is like the LB back, right? So this is one of the famous robots that we know, but I'm sure that robots will be back. So I'm going to stop here on